our goal today is to cover the highlights of virtual memory. And then over the long weekend, we'll post a final version of the study guide. I'm working on a draft right now, but we'll have the key ideas for memory management and virtual memory in a single short study guide for your reference. And we'll have the Module 4 solution posted where you delegate initial and maximum virtual memory so that you can see how that affects the performance of your own system. And that'll be like a quick review of optimizing your personal technology, but you'll also be able to see what effect modifying virtual memory settings in an OS can do in terms of performance. And then as we start early next week, we'll have an assessment out for the module so you can log your first attempt. We'll also post the final version of the retake for module 3. And yeah, so the main topics for virtual memory include background process and applications, demand paging, copy on write, page replacement, allocation of frames, thrashing, which is something that is a serious problem on servers. So memory mapped files, allocating kernel memory and other considerations, and then operating system examples. Our intention for the module solution is to give you a direct first-hand experience with an operating system example. So that's one reason why we're doing this. The objectives today, you want to be able to describe the benefits of a virtual memory system, explain the concepts of demand paging, page replacement algorithms, and allocation of page frames, discuss the principle of the working set model, examine the relationship between shared memory and memory mapped files, and explore how kernel memory is managed. So in terms of a quick background, essentially code needs to be in memory to execute. That's the basic understanding we need to keep in the forefront. We can't execute code directly from a disk, right? That becomes a problem. Unless, of course, we're dealing with an innovation like Optane or 3D XPoint, where the RAM and the solid state memory structure is one and the same. And in a few short years, this whole convention of working may fall to the wayside. But for now, so long as the von Neumann model of computing holds true, essentially you always have to move something into random memory in order to be able to execute it. But the truth is that an entire program is rarely used. So if you think about the 80-20 rule, if you open up an Excel spreadsheet or a Access database or a PowerPoint, there's a lot of features. A lot of the program is never used. And for that reason, you can load an awful lot of stuff that's extraneous, right? So you have large data structures, and the entire program code is not needed at the same time. And this creates challenges. So you have to be able to partially load and execute a program, and then other parts of the program on demand. And each program takes less memory while it's running. More programs can run at the same time. So if you can partially load a program, then a program is no longer constrained by the limits of physical memory. So this is the whole rationale for a virtual memory system, is that if you need to be able to partially load a program and you're able to do that, then the limits of the memory size you have are no longer a constraint as far as just being able to get a program started and using it. Any questions about that? So If you can partially load programs, then each program takes up less memory, which means you can multitask and load more programs simultaneously. Less I/O needed to load or swap programs into memory. Each user program runs faster. That's only true for the case where the extra features and the entire program code isn't used, right? So under that premise, there's lots of advantages for virtual memory. So what we're doing is separating user logical memory from physical memory. Only, as we've stated, only part of the program needs to be in memory for execution. The logical address space can be much larger. So yeah, this is just a basic restatement of what we just walked through. The virtual address space is a logical view of how a running process is stored in memory. It usually starts at address 0 with contiguous addresses until the end of that space. However, with fragmentation, like we've seen in memory management, that's always a challenge. We'll get to that in a minute. The memory management unit is involved in that process as well. And basically, virtual memory can be implemented by two different methods, one called demand paging and demand segmentation. Any questions so far?
Not for me.
So this is one of those screen captures I'm probably going to include, along with the study guide. This is one of those diagrams that I really want you to become familiar with. It's a great way of showing what virtual memory really is. So virtual memory can be huge and limited only by the size of the available disk space and the configuration of the virtual memory. So for servers where you're working hundreds or even thousands of users, virtual memory is a godsend because it allows you to basically work on a whole different level. So you still have logical memory shown here with virtual memory and a memory map, but essentially the magic happens between physical RAM and the hard disk. So there are cases where pages are written out to the disk in between the RAM and the disk, right? And that's what this is showing. Any questions about this diagram? Your virtual address space works like other memory management conventions. You have stack and heap. And as the size of stack and heap change, this available memory can shrink, right? So it says the unused address space between the two is a whole. No physical memory needed until the heap or the stack grows to a given new page. So the one point on this slide to remember is that when you're designing the logical address space, you start with the max and work your way down. So you allocate for a maximum scenario. The advantage of this is you do have holes that allow for growth as you read and write dynamic link libraries. And here it says pages can be shared during fork, speeding the process creation. So if you remember, fork is a way to spawn processes. So you can share pages in virtual memory when fork is active, and that helps with process management as well. So ultimately, when you're talking about virtual memory management and traditional memory management, those are intended aspects of the operating system internals, because ultimately it all gets back to the process, right? So a running process. So here you see a basic diagram of how You can have shared pages of memory in between shared libraries in virtual memory segments. And when you're dealing with a multi-user, multitasking system like a server, again, with hundreds or even thousands of users, there can be huge advantages. Think of a common set of web pages that users are accessing and refreshing all the time, right? So let's take a look at demand paging first. So what we're talking about is paging virtual memory, swapping in and out on demand. So you could bring the entire process into memory at load time, or you could bring a page of memory in only as it's needed, right? So this aspect of demand paging allows for that flexibility where an entire program doesn't need to be loaded when it started. So the thing to remember here is that you do have some challenges when you're swapping pages in and out. In some cases, you have an invalid reference, so there is some basic overhead when it comes to error management. This part of it I find really humorous. So the lazy swapper, the lazy swapper is a component of demand paging. So those seem to be contradictory interests, right? So you have demand paging where you need something, but in extreme cases, it never swaps a page unless a page will be needed. So the lazy swapper only demands a page in the case where it's needed. Otherwise, the lazy swapper doesn't request that code and memory page. So a swapper that deals with pages is called a pager. So that's a basic definition. So you could say that a lazy swapper is a lazy pager. Are there any questions about this?
No questions.
Okay. So with demand paging, the basic concepts to consider are that with swapping, pager guesses which pages will be used before swapping out again. Now, a lot of that would tend to flow in terms of the design of the software application, the arrangement of menus. I mean, if you're in a proofreading ribbon in Microsoft Word, the odds are pretty good that the features and functionality of proofreading would be engaged sooner than the other feature modules in the ribbons. Does everybody understand what I'm talking about? So can everybody see the ribbons at the
Yeah.
top of my screen? So you have these menu choices, and as these are displayed, if software is appropriately engineered, as users engage different aspects of the GUI, there could be very simple associations for which features are likely needed sooner instead of later, right? I'm just calling this out because it's kind of a logical extension of what we were just looking at in that slide. So if I'm in the slideshow menu, I'm going to be doing things with these features, and basically your pager is guessing which pages will be used before swapping in and out. So there's a lot of back-end stuff with applications, system calls and APIs that can include these kinds of criteria so that the demand paging works more efficiently. All right. So pages that are needed are already resident in memory. So the MMU functionality is critical in order for this thing to work smoothly. But that's kind of an intuitive thought, right? So if you have a hardware component that's involved in memory management, that hardware component would have to have features and functionality to gauge the attributes and criteria for imminent use as opposed to dormant state. If a page is needed and not in memory resident and not memory resident, there's a detection and load process that needs to trigger. And you need to be able to queue it up without changing the program behavior. So a user could or could not engage a certain feature, right? And the programmer doesn't need to have to change the code in order to be able to do that. So if you ever wondered why there are millions of lines of code in Windows, this is one reason why. It's kind of like a giant chess game where people are anticipating common use, routine features and functionality versus seldom used or rarely utilized resources. This is kind of a favorite concept of mine. The idea of, so OSs are most efficient when they're working on the bit level. So we have a thing in file systems you're going to learn about called an archive bit. An archive bit is a single bit that signals whether or not a data file has changed or remains unchanged. And it's just an on or an off. It's a bit, and that's all. So 1 or a 0. And for virtual memory, they have a valid invalid bit, which is associated with the page table. Remember that frames have to do with physical memory and pages have to do with logical memory, right? And one of the key components in the middle is this idea of a page table. And part of the attributes that are tracked in a page table is this idea that something is either in memory or not in memory. V would mean that it's that particular frame and page is active in memory. I would mean not in memory. I could mean idle in this case, right? Not really sure what the V means. Could mean volatile. It's in volatile memory, and I means it's idle, so it's in disk memory. And not, well, in this case, they're saying it's invalid or valid is what it means. So invalid means it is not in memory. Valid means it is loaded in memory. So the bit signals, yep, this is a valid memory page. That means it's loaded in memory. This is an invalid memory page. That means it's not loaded in memory. Are there any questions about V and I? I was just working some deep processing with other word associations or concept associations to keep in straight, right? I does not mean I for in memory. V does not mean, V means it's in virtual memory, meaning it's not in active memory. It's actually the reverse. It would be easy to get the I and the V flipped because it's the first letter of the reverse case. Does that make sense? I am going to try to trick you on an assessment about this, right? I'm going to say, oh, you have a memory frame. Select everything that's true about this statement. And one is, okay, it's physical memory because you're talking about a frame. And then, okay, it's not loaded in memory because the valid invalid bit is listed as I, right? Everybody got that? So here's basically it's how this concept would fit in for a case where it's used. So you can see here that in terms of physical memory, you have frames A, C, and F. And where you have frames A, C, and F, physical memory is extended into the logical memory, right? the paging, and A, C, and F are 0, 2, and 5. So here you see on the page table, right, 0V, it's in memory, it's in memory, it's in memory. But what about all the others? They're not in memory. They're still stored in the virtual in the backend store, right? Does everybody understand what I just walked through? Getting crickets. Are we still there? Are you guys still in the mix?
Yes, I understand.
Okay.
Yeah.
Okay. Just want to make sure we wasn't off in la la land by myself. Page fault, right? So you can have challenges with the use of virtual memory or page memory, right? If there is a reference to a page, first reference to that page will trap the operating system. So there is some error correction, and so the idea of a page fault is a method to perform error correction and remediation. So the idea is to identify an issue and then find a free frame and then swap out so that the instruction can proceed without delay. Let's see how this works. So you have a common reference, you discover that there's an issue. Well, you have a common reference and you discover that it's not in memory. So this is trapped through the operating system. There's a page recovered from virtual memory, which is brought back to restore the missing page. And then that cycles back into a reset of the page table because now you have the rest of the instruction, right? And now you can restart the instruction. So that sequence is a way of handling page faults. So what insight have we gained here? When you hear about a page fault, you're talking about a case where a program needs to execute and there's pages of the code missing. That's because of the virtual memory convention. Not all of the required code is handy, and so this is the process under demand paging that a page fault is resolved, right? And this happens quite frequently. So handling page faults doesn't mean that something's wrong. It means that we're handling issues where a page is missing and we're restoring the page that's needed because now we're accessing new features and functionality. And then the page table is reset and off you go and you're on there. This happens in the blink of an eye. Any questions about this page fault process? So there are cases to consider with demand paging. And so there are cases where you start the process and there's no pages in memory, right? So in a case like this, everything is demanded all at once. So there's this approach to handling scenarios like this where and they call it pure demand paging, right? So when would that happen? Well, when you're maxed out with your available resources and you start, an application that requires a huge demand of memory. So so there are some aspects to this that make that more efficient. There's mention of the locality of reference, but the main thing to remember when you see this concept about pure demand paging, it's about a scenario where a process starts and there's nothing preloaded, right? So you have an on-demand scenario that's nothing's preloaded because the software is something that's infrequently used, perhaps. So in order to support the demand paging, this is just a summary of what we've talked about. You have to have some way of tracking what's loaded and isn't loaded. That's the valid invalid bit. You have to be able to deal with secondary memory when you're swapping stuff in and out, when you have page faults. And you have to be able to restart the instruction after the requisite code has been loaded. Any questions? And that's the hardware support that's needed. So the MMU has to be capable of working these three basic essentials. When you talk about restarting an instruction, there are cases where you have partial overlap of the code. That's something you have to deal with on occasion. And so there are questions about algorithms, whether it's better to restart the whole operation. So there are cases where demand paging performance isn't all that good. And if anything, while we're walking through the weeds of virtual memory methods, it should become abundantly clear why there would be an advantage to establishing initial and maximum virtual memory, disk memory, that matches the size of the entire physical RAM address space. I mean, that's the goal here, is so that after we thrash through the leaves, the weeds, that you'll have a deeper appreciation for how this one performance enhancement can pay big dividends. And it's almost the kind of thing where you'd wonder, okay, why doesn't an operating system just do that in the first place? I think back in the day, decades ago, when users weren't so crazy about multitasking and having so many tabs in a browser open simultaneously, was a simpler world. And this is one area where I think OS design could catch up. And in my professional opinion, I've rarely seen a case in 20 years where a system couldn't benefit from establishing fixed initial size and maximum size to match the amount of available RAM. So anyway, let's see what's important or relevant about this. So in a worst case scenario, when demand paging is taxed to the max, you have queues and latency time, and guess there's like a tipping point where the overhead gets to be pretty extreme. So these are additional considerations. So the amount of interrupts and I/O increases considerably. There's a lot of wait time incurred with a CPU. So this concept of effective access time, you could have portions of an application that are available. The rest has to be loaded. There's all this overhead and interrupts. The overhead is measured with this criteria called effective access time. So by the time you add all of the rest of the hoops you're jumping through, that can be significant. That's why when you're optimizing your personal technology, you defragment your hard drive, because when it's reading a single contiguous available space of disk, the performance turnaround is greatly reduced and the effective access time is much faster. So I hope that makes sense. I am not, basically the effective access time has to do with the amount of time it takes to access the memory, the page fault overhead, where there's swaps in and out. So from what we've previously reviewed on the diagrams, I hope that makes sense. Just remember it's the memory access, but then you also have the additional time it takes to run that. I don't anticipate that I would have an assessment item where I ask you to calculate the EAT based on a scenario. But I do want you to be aware that the effective access time includes not just what's happening with memory frames that are loaded in memory, but also the back end with faults, okay? So it says if one access out of 1,000 causes a page fault, then there's a tremendous slowdown. Put another way, the reason that you do disk optimization and disk defragmentation is because the more your file is fragmented, the greater the occurrence of page faults where something is supposed to be there and it's not there and the instruction can't fire, so you have to go out to physical disk memory and then retrieve it and then reset your execution, right? 8.2 microseconds. Now that may not seem like a big deal, but it doesn't take long for disk fragmentation to really cause a huge problem. And what you're going to find is that computer owners, after what, 18 months, 2 years, 3 years, things slow down on a system, right? Hasn't that been your experience? Intuitively, let's just talk about this a second. Over time, isn't it true that things just get slower and slower on your laptop unless you perform maintenance, right? Unless you do some things. So the reason that disk optimization and defragmentation is so much of an advantage is because it does have a big impact on EAT, right? So these are some more statistics about performance degradation. You want it less than 10%. There are different demand paging optimizations based on different operating systems. What are the most relevant things you need to know about Linux and BSD Unix? Yeah, I can't think of any I'd require you to know. But here it says swap space IO is faster than file system IO, even if on the same device. So what are we saying? Virtual memory prioritization and performance in most operating systems is rigged so that it takes priority over traditional file system input and output, right? By design. This is a useful fact here. Mobile systems don't typically support swapping. Instead, they demand page from the file system and reclaim read-only pages such as code. So there's a watered down version of this, but they don't typically work demand paging like desktop and server operating systems. So copy on write allows both the parent and the child processes to initially share the same pages in memory. So this is an adaptation that can help virtualization, virtual memory work more efficiently. You just need to understand how the concept works, copy on write. So there's a copy of something that's written so that you have two copies, one for the parent, one for the child. Any questions about copy on write and what it is? So this is a convention that helps with fork when you have parent-child processes, right? So copy on write would help with this aspect of process management. So this is just an example of how copy on write works, and that the two processes, parent and child, if we assume that process 2 is the child and process 1 is the parent, you have well, no, before copy on write, you'd have each of these accessing physical memory, but if each have their own copy, it's more efficient. So you have a challenge here where one process is using the common memory and then there's a change, right? So you have algorithms to help if there's no free frame available. So overallocation, corruption of bits. This is one thing that it's part of the finer points of virtual memory. Basic page replacement if you have corruption, right? So in terms of algorithms, you can work on the frame level or page level. And yeah, you have intermediate components like reference strings. So and this shows how there's a relationship between the number of frames and the number of page faults. One of the algorithms is called first in, first out. Let's see what else. I would ask you to be familiar with the idea of first in, first out as an algorithm for remediating demand page problems. Another algorithm they mention explicitly is this idea of the optimal algorithm. So you replace a page that will not be used for the longest period of time. 9 is optimal. So there's deliberate page replacement based on the level of use. Least recently used algorithm. So you have basically the reverse of that. So it says it's better than first in, first out, but worse than OPT. That based on the scenario, right? So which algorithm is best depends on the scenario. Let's see, what else do we need to know about this? I'm going to basically extract out of here what it is that's relevant for you to know for the algorithms. So yeah, here's another concept, second chance page replacement algorithm. It's clock driven. So it's sequence driven based on the order. So instead of sequence-based algorithms, you also have counting algorithms, least frequently used and most frequently used. It replaces the page with the smallest count as opposed to the largest count. if I ask you the question, which one's better? The common answer is it depends on the scenario. And then there are page buffering algorithms. So in the middle of all this, you can have buffers or caches that can help improve efficiency. Raw disk mode. So does anyone remember something called direct memory access, DMA?
Yes.
Yeah, you can take a direct flight between RAM and disk. Yeah, so there are adaptions and conventions that help with the virtual memory process. And when we talk about how virtual memory operations, reads and writes, input and output, has a higher priority and it's higher performance than standard file system IO and reads and writes. That's one piece of it, right? So when it comes to raw disk mode, virtual memory operations take priority. And this has been around a long time. The IBM 370 is a mainframe that's been around an awful long time. I think it's safe to say that some of these IBM mainframes have been around almost as long as I have and before you were born. So I'm not sure exactly how, I guess they're providing some history about how some of this came about. Mainframe memory was very expensive and virtual memory was an interest because it helped resolve a lot of very expensive inefficiencies on a mainframe. So the idea of virtual memory allocations equal or proportional, meaning flexes with the conditions, or is prioritized. You can also allocate virtual memory globally and locally, depending on other hardware resources and operating system conventions. This term NUMA, non-uniform memory access, it's this idea that all memory is considered equal. No, it's the reverse of that, non-uniform memory access. So this is another virtual memory method that accounts for the distance and how far something is close, how far something is from memory versus the size of the system bus and so on. So for some operating systems, NUMA helps with virtual memory utilization because it takes into account the physical distances and stuff like this. Although I'll be honest with you, I don't have a lot of background or experience with this particular concept. Oh, that's why. Solaris. So in the 25 years I've been working with servers, I have not had direct experience with $100,000 Solaris systems. For me, it would be standard servers that you get from Dell that would be my wheelhouse, and that's one reason why NUMA is not something that I've encountered or done a lot. Now, this is something I've seen a lot. And I'm glad we're on this topic as we bring our class to a close. So thrashing is a huge issue. If you have virtual memory challenges that remain unresolved, disk thrashing is a state where there is needless exchanges between RAM and virtual memory. And when these things swap in and out, what happens is that the disk reads and writes go through the roof. You can ruin hard disk arrays in a very short period of time, where conditions that cause thrashing remain unresolved. On servers in particular, with hundreds or thousands of users, this notion of routine maintenance and, system optimization, defragmentation and maintenance, it means the difference between replacing a server within a single calendar year, or at least the server disks. And when your disks are reading and writing so furiously that they start to corrupt the data and they crash, it causes all sorts of, it's a kind of a domino effect. It causes more overhead on the part of personnel, and so they have to spend more time replacing disks and arrays. They have to rebuild storage volumes. It gets to be bad. So the idea of optimizing virtual memory, I can't emphasize enough how much benefit there is, which is why I'd like to stop sharing at this point and stop recording.